thanks again for having us for the panel. Oh, sorry, I'm trying to. All right, so we're going to roughly keep with the format that previous speakers have so usefully employed for the panel, where we each present, although you have all of us in the flesh, so I guess you can ask us more. But we're each going to present a few slides, and then we'll in turn, and then we'll have some discussion. And so I'm going first. Let's get started. We heard a bit about hydrodynamics and transport in Andy's talk this morning. So I don't have too much to, I wanted to start off with a little bit of history about hydrodynamics and why it's a useful perspective that we all share to bear in mind when thinking about these exotic systems that we're confronted with in the study of ultra quantum matter. But let me summarize kind of the highlights here. The main starting point for us is that many very complicated microscopic systems that we cannot solve with known methods, they share a feature in common, which is that they thermalize. And as a result of that thermalization, they have a very simple long wavelength effective description at finite temperature that we might call hydrodynamics, as Andy did earlier today. This is a robust fact for a very wide range of systems, ranging from billiard balls to ADS CFT and black holes. The things I want to focus on are the robustness, the simplicity of these effective descriptions, and the way in which all of the details of the potentially strong correlations that underlie it are subsumed into coupling constants of these very simple effective field theories or effective descriptions. In these models, these models of transport, the relevant degrees of freedom are merely those densities for conserved quantities. And the ensuing description, what one means by this effective description, is very tightly constrained by symmetries of the problem, which is very nice for us. It's one of the few things that we know from the get-go when talking about these strongly correlated systems. We heard a little bit about how, in Landau, for instance, how you would go about the business of constructing hydrodynamics, where you have some degrees of freedom, you take your symmetry currents, and you postulate some expression for symmetry currents in terms of an expansion in those variables. And that procedure, it's analogous to what one does in Wilsonian effective field theory. It is a little bit different. Instead of a Lagrangian expressed in terms of gradient expansion of the degrees of freedom, you have constitutive relations. You say T mu nu equals, and then you write down some expression with coefficients, transport coefficients, that have to be matched to microscopics, but from the effective field theory point of view, or effective description rather, you can just think of as things to be fitted either from microscopics or from data. But they play the role basically of coupling constants. This phenomenological treatment is extremely useful, has been very useful, will still be very useful in the future. It is not complete. It's not an effective field theory. In particular, when it comes to treating loop corrections that arise from fluctuations of the fluid degrees of freedom, you need something more sophisticated. And there have been various phenomenological attempts over the years to discuss that go by names like stochastic hydrodynamics or fluctuating hydrodynamics. But there is a more modern approach to resolving those issues that I'll talk about now, and also kind of appeared implicitly in Andy's talk. So a more modern approach is not the only thing that's useful, but something that you can do that will allow you to tackle these problems of loops is to build a genuine Wilsonian effective field theory for hydrodynamics or for transport, where the crucial ingredient, the thing that allows you to tackle the fact that you have dissipation using a Lagrangian, is that you're building effective field theory for a mixed state, for a density matrix, not for the vacuum. And these effective field theories, I guess I did an extremely poor job of references. There are no references in my slides, come to think of it. This approach was really, it has an origin story, but its more modern form where things were really nailed down appeared in the last few years in papers of Hong Wu and Paulo and Michael Crossley, and also Mukund and Loga and Felix Heil, and then also some papers of myself and Amos Jerome and collaborators. Because you time evolve a density matrix, you have a more complicated time contour. You have what's called a closed time path contour. You associated with this, you have the doubling of degrees of freedom, complicated Lagrangians, but also additional symmetries beyond the usual ones. And at the end of the day, you can build, using those symmetries, very tightly constrained effective field theories for dissipative hydrodynamics. And at some very basic level, these theories, they're kind of like sigma models. And that's history. There are some interesting directions within that paradigm, maybe closer to the history, that I think we'll hear a little bit more about from my other panelists briefly. But for the rest of my portion, I'd like to focus on a topic that maybe has more to do with the focus of this particular meeting. And that is hydrodynamics with exotic symmetry, where exotic means,
something you didn't think about before.
Yeah, as a loose definition. So a few thoughts. So already in Andy's talk, we saw a very nice discussion about descriptions of systems with dipole symmetry. One can, of course, widen one's gaze to think about systems with subsystem symmetry, which is going to be much more intricate, I would expect. But there, there's basic questions. If we're going to talk about transporting these models, we need to assume from the get-go that they thermalize. But to what extent is this true? There's, to my knowledge, less work on the chaoticity and finite temperature aspects of interacting models of fractons that would address that. That's an important microscopic input that needs to be addressed. But assuming that they do, or at least if one focuses one's efforts on those systems that are chaotic, that do thermalize, there's a number of questions that arise beyond the simple construction of the hydrodynamic description as informed by symmetry. For instance, a theme that appeared in the panel yesterday was the fact that in models with fractons, or in models with these exotic symmetries, that you can have UV-IR mixing. And one might wonder, does that leave any imprint on the hydrodynamics? The hydrodynamic sigma models that one gets using methods that Andy was talking about, and they do have this feature. There is really some UV-IR mixing, or at least the prospect of it, hiding behind the scenes. And there's a physical question, whether or not these enormous number of extra states, UV-sensitive spectrum of states, whether or not they lead to any interesting physics in the transport or at long wavelengths. If you consider some analogs of viscosity and you consider loop corrections due to hydro modes, are all of these funny low energy states, are they exchanged in those processes? Do they lead to, if they don't, that's interesting. That would mean that the hydro is closer to that of conventional quantum field theory, even though there's UV-IR mixing. And if they are exchanged, it's also interesting, because now you see in potentially measurable transport phenomena, you might see indications of the mixing. More broadly, I think this is an extremely interesting direction for more people to study, because this is a place where we might not be able to solve the strong interactions. We might not be able to deal exactly with the underlying microscopic systems, but yet you can make predictions for what you would see that would be unique to these symmetry classes. You might be able to find a slab of material, a hot slab, and say, well, you would at least it has these symmetries, and maybe it has fractons. Another comment is that in the history of transport for relativistic systems, there's a lovely fact that 't Hooft anomalies can fix certain transport coefficients that leads to observable physics, chiral transport phenomena, for instance, in 4 dimensions. And while there are instances of there are lattice models with fractons with these exotic symmetries that do have certain anomalies. And you might wonder if these anomalies can leave any imprint on the transport. Can they be measured? Maybe not.
We're working on this.
See, these are good questions. So what about here? This is something I think that, okay, Nadi was teasing people a little bit yesterday in the panel, saying that there were some things that could have been discussed in other panels that weren't in those things, but he mentioned them. Well, I could, okay, he's not here to defend himself, but I could tease him a little bit back and say that the more broadly questions of 't Hooft anomalies in these in models of fractons is an extreme on their cousin of anomalies, topological terms. This seems like an extremely ripe direction purely on quantum field theory grounds. The prospect of this in hydro gives you another way to think about them and observable physical consequences, perhaps. Maybe. Another comment that is related to things that appeared earlier today and things that I've thought about as well is that in the usual old story of hydroeffective field theory, and by old story, I mean this thing is actually not so old, of like 2015 to 2017. I guess my oldest child would think that's old, but that program, it really simplifies dramatically. You don't need to do this, but it's much easier to implement when you know how to couple your underlying system to a weakly curved, so slowly varying weakly curve, but fixed background spacetime. And there's a question of whether or not there are similar constructions, even when we have these exotic symmetries that could simplify the procedure of constructing hydrodynamics or hydrodynamics effective field theories that account for dissipation. I think with the dipole symmetry, there may be some, it may take a little while before this is completely settled, but there does appear to be a way to couple systems with dipole symmetry to background. But subsystem, well, that maybe is a frontier for future work. And the reason, I guess, why this has anything to do with hydro is that in a background spacetime, what is it conjugate to? It's conjugate to stress tensor, the symmetry current that's participating in the hydro. So if you want to talk about response functions of the stress tensor as encoded in the hydrodynamics, well, you're effectively turning on sources, you're effectively turning on perturbations in the background spacetime. And how does one do that carefully, systematically, and so on with these exotic symmetries is an open question. And the last comment that I'll include on this slide is that a pivotal player in these modern treatments of hydrodynamics has been holographic duality, so things like ADS-CFT. What happens, if we talk about the transport of systems with strong correlations, how do you do that? And from first principles, well, usually you can't. But in theories with a gravity dual, you can, because the strong interactions are completely reorganized. They're geometrized into very simple physics, that of black holes in semi-classical gravity. And well, so there one can get hydro, and one can, even formulate effective field theories, and so on and so forth. And we can ask, in the context of systems with exotic symmetry, can we find, well, not necessarily holographic duals, maybe that's asking for too much, but at least gravitational effective field theories with the same symmetry pattern. Naively, this is, maybe you can find black holes to do the job, but finding the theories of gravity, that's going to be the tricky thing, because Matt, in the usual holographic dictionary, boundary global symmetries are dual to bulk gauge symmetries. And now you can imagine gauging something like subsystem and then having a theory of gravity invariant under it. And what on earth does that look like? This is a panel, so I can pose such questions that I have no idea how to answer, and let all of you judge if they're worthwhile and to think about them, perhaps, if they are. That's all I have to say. Oh, no, it's not all I have to say. One more slide. So the vision, I guess, that is perhaps too implicit in what I'm saying is that why are we all up here talking about hydro? It's another window into the dynamics of these systems that's strongly constrained by symmetry, which we know from the get-go, that evades the problem of having to solve the dynamics of strongly correlated systems, which we in general do not know how to do. We don't know how to deal with the interactions. This gives us another window into the problem. And one of my hopes in the long run is that this really will give us a workaround to be able to discover these exotic systems in nature, actual experiment, through hopefully universal aspects of the many-body transport. And I think we're already seeing some fruit of that along the lines of what Andy was saying earlier today, and I hope there's a lot more. Thank you.
Should I continue or?
So if there are immediate questions to express, otherwise,
Let me share the screen. Okay, so I will pick up from what Kristan has ended his talk by emphasizing again that hydrodynamics is typically simpler than quantum field theory or conformal field theory or many-body theory that underlies the system. Sometimes we don't have to understand all the details of zero temperature physics in order to write down an effective description of finite temperature system at distances that are large compared to the, say, mean-free path. So there are a few systems, example of a system where I think would be interesting to try to understand. So for my favorite system is charge particle in high magnetic fields. We know that if the magnetic field is high, if the energy scale of the system is low, for example, if the temperature in the system is low, then all these charged particles will be located in a single Landau level. This is a situation that can be realized in condensed matter system, gallium arsenide in high magnetic field, but it seems to be more widespread in nature. For example, if you look at the typical scale of magnetic field in astrophysical plasma, then in many cases the electrons there would have should be in a single Landau level. And so one can ask, what is the hydrodynamics and kinetic theory of this system? Do we understand how to write down hydrodynamics of particles that are constrained to move on a single Landau level? And this question may be related to exotic symmetry, as one can illustrate very easily. So if I take a system of non-relativistic particle in a magnetic field, then we see there are two conservation laws that I've written down here. There are actually three. I neglected the conservation of energy, but conservation of current, say dρ over dt plus gradient of J equal to 0. The conservation of momentum, actually non-conservation of momentum, say that the change of the momentum density of a given volume goes through the divergence of the stress tensor and the Lorentz force acting in the system. Since we are in a high magnetic field, this term is going to be important. In particular, when the momentum, when we are focused our attention on the low energy regime, low frequency regime, the time derivative term here is negligible compared to the term with no derivative. So the second equation suddenly becomes not a conservation equation, but a constraint equation that says that the current is tied to the divergence of the stress tensor. So I'm suppressing here all the indices. One can easily restore them and say that J is equal to 1 over the magnetic field time derivative of the stress tensor. Now one can put that into the equation for the conservation of charge and convince ourselves that this equation looks like an equation that would come out from a higher rank symmetry. Rho over dt plus second derivative of the stress tensor is equal to 0. So in a very simple system, just charged particle in a magnetic field, if we are in the low enough energy regime, we effectively have to deal with a system with one type of exotic symmetry, higher rank, higher rank conservation law. So as far as I know, we do not understand. There is no, they still have not been a complete, a final word on how hydrodynamics should work in such a system. In particular, could there be subdiffusions? And my inclination would be to say yes, but in this system, there is an extra conservation law, that is energy conservation, that leads to heat transport. And I'm not completely sure I understand heat transport in such a system. Should heat transport also be subdiffusive, or there could be some just simple diffusion of heat? Clearly, here the situation is more complicated, because we also have the whole transport coefficient. For example, the transport of heat might happen also in the direction perpendicular to the gradient of the temperature, in addition to the term in the constitutive relation that says that the heat can transport along the direction of the gradient. So all these have to be thought of. One of the regimes that should be that sounds interesting, but seems to be quite non-trivial, is the regime of high temperature. So typically, when people talk about the quantum Hall effect, they distinguish two energy scales. One energy scale is the Coulomb interaction between the electrons, and another energy scale is the distance in energy between neighboring and Landau levels. So imagine that we have a temperature that is high compared to the energy, the interaction energy within the Landau level, but still low compared to the space distance to the next Landau level. It is just an interesting regime to consider, in which, from the point of view of the lowest Landau level physics, the temperature is almost infinite, but but there is no kinetic energy. All the non-trivial physics is due to the interaction between the electrons. So here we have a situation very somewhat reminds me of Kristan's talk today, when we have a field theory with no kinetic. The kinetic term is local in space, but all the transport in the system must come through the interaction. The last point in this slides might be a bit more speculative. We know that there are condensed matter systems with flat bands, so these are systems which are similar to lowest Landau level system, in the sense that the kinetic energy of the electrons are completely quenched. There is no dependence of energy on the momentum. Is there interesting electron hydrodynamics in such a system? And then here on the last slide, I collect some different, maybe unrelated set of questions. One question has been mentioned by Kristan. Are there a holographic model of system with exotic symmetry? Maybe that's an interesting question also from the point of view of the bulk, whether we can realize this exotic symmetry as some higher rank, say, gauge theory in the bulk, and understand the hydrodynamics in that way. Is there interesting undiscovered properties of hydrodynamics of near non-trivial phase transition? Like, for example, the BKT phase transition is a phase transition that is not captured by the standard Ginzburg-Landau formalism. And so how does dynamics work in such a system? Is there non-trivial hydrodynamics in non-Fermi liquids, where the field theory of non-Fermi liquids is still not understood, but as a rule, hydrodynamics may be simpler than field theory. Maybe there is a non-trivial hydrodynamics of non-Fermi liquids. And that might be related to the last point here. Generalized hydrodynamics with infinite number of conservation laws this seems to be an active area of research, and so I've just put this point here, but without a question, maybe because I don't know if there are actually unsolved interesting question in this area, but this is something that might be related to the hydrodynamics of non-Fermi liquids. So let me stop here. Pass to Andy.
Are there further questions? If not, I guess book.
Yeah, so I'll maybe try to be somewhat brief relative to the, just so we can get a discussion going. So I think Kristan and San have nicely sort of set up the broad theme for this discussion. I thought maybe one thing that would be useful to emphasize is that there's really sort of a celebrated history of hydrodynamics, both in ancestral times and in modern times. So we first think about hydrodynamics when we think about liquids like water, and then maybe in high school or college, you learn that air also obeys the same hydrodynamic equations, and that's been known for probably a few centuries. And then when you get to grad school, you learn that there are other interesting hydrodynamic systems. Now, actually, perhaps in all three of these examples that I've displayed on the page, the equations are also the same as in the previous two, up to some silly generalizations like Lorentz versus Galilean symmetry, et cetera. But in heavy ion collisions, you can see if you ask about the distribution of particles that you detect, it's not compatible with just a bunch of free streaming kind of recombined quarks and gluons. There's evidence for a sort of intermediate window where this fireball expands as a fluid. In ultra cold atoms, you can do experiments where you have a bunch of strongly interacting fermionic atoms in a trap, and you just let the trap go. And you can ask, do all of the atoms basically fly off as ballistic non-interacting particles? And again, the answer is no. You find that for some time, this cloud sort of expands as a fluid. And everything I'm talking about here, I mean, these are experiments that have been done. And then most recently, this was sort of where I got some fame or infamy, is thinking about hydrodynamics of electrons in graphene, although other solids in principle could work just as well. So here, basically you have a crystal with very, very few impurities, and the momentum in the electronic system can be long-lived, and so there can be really viscous hydrodynamics of electrons. One thing you have to be careful about is that I think perhaps one ought to think of all solids as having hydrodynamics. It's just ohmic transport. But people get quite offended if you say that. So you need to just watch what you say. But we're now seeing viscous Navier-Stokes equations at least sort of begin to arise in graphene. Okay, so all of those are experimental questions. And I think as physicists, it's good to have in mind sort of what is going on in experiments, especially in condensed matter physics. This is sort of helpful for getting a job. But I'd also like to point out, since probably this is a theoretical audience, that I think there's a lot of reasons to be interested in hydrodynamics purely on theory grounds. And so Kristan has already sort of emphasized some of the recent history in his discussion of where hydrodynamics comes from as an EFT, and this sort of beautiful story that, at least for thermal systems, was arguably concluded in large part in the past few years. really thinking about a kind of geometric Schwinger-Keldysh construction of an action for the Navier-Stokes equations. And I think this solved a 100-year-old problem of how to write down an action for Navier-Stokes. So where do we go from here? I've put down 3 bullet points that interest me personally, but I think they should also interest other people, I hope. The simplest one that I put down are reduced space-time symmetries. This is something that I think we've been working on in my group now for a few years, and maybe we're starting to wrap up, but it would be nice to realize these things in the lab somewhere. So you can, for example, think about anisotropic electron liquids. There can be sort of funny viscosity coefficients that really don't have analogs in any of the other fluid settings that people have looked at. More recently, we're thinking about systems with helical symmetries and other kind of exotic symmetries mixing translation and rotation. And this has some kind of curious effects that are somewhat reminiscent of anomalies. In my talk this morning, I talked a lot about exotic conservation laws, which we branded as Fracton hydrodynamics. And something I'd like to think about in the coming few years are sort of really non-thermal systems. So anything from just a sort of precise characterization of the Markov chains that we use to simulate dipole conserving fluids to more crazy examples of non-thermal systems like flocking birds, where there's definitely no notion of temperature that's relevant. Now, I don't feel too guilty at this point because I think Kristan did the same thing. But in Landau's paradigm, to sort of tell a historically revisionist story perhaps, but the way that this one proceeded with hydrodynamics was you just wrote down the most general constitutive relation you could at the level of the equations of motion. And if you have no derivatives, you try to be a little more careful and match thermodynamics. And then you need to make sure that there's dissipation and somehow you don't have like a blow up where the diffusion constant is negative. But other than that, you can do whatever you want. And I hope that this morning I was able to sort of emphasize that we're already seeing that this is not good enough. In the Fracton hydro world, you really just get the wrong answer if you use this approach. And we've done simulations, which I don't think we've published anywhere, but you indeed cannot find the Fick's law of diffusion no matter what you do in a dipole conserving system. And so I think we already sort of know that we need a better understanding of hydrodynamics as an EFT. For thermal systems, we have it, but I think for more general systems, it's still missing. And so sort of looking forward, I think that one reason to care about these questions is what both other panelists have also mentioned. A good understanding of hydrodynamics really leads to sort of concrete predictions for experiments. And even independently of that, it allows us to really better understand commonalities between diverse systems. So my favorite example of this is that there were in the literature a couple examples that we knew of back in 2020 when we got started thinking about these problems, where we found sort of this fourth order subdiffusion equation. And I think it was a little mysterious. It always seemed to show up kind of accidentally. So in a tilted optical lattice, I talked about this experiment this morning where you can see this k to the 4 scaling. But also if you just take, I put here quantum Hall, I guess because I'm trying to get more people interested. But even if you put classical charged particles in the magnetic field, there's an old paper of Sun and my advisor and a few other people where they sort of note in an appendix that if you look at the normal modes of a charged fluid in a magnetic field, the charged mode actually has subdiffusive decay. And this can be traced to a similar, there's basically a common sort of origin of an emergent dipole conservation in both systems. And so I think this is really, if nothing else, this whole business of Fracton hydro is helping us to explain maybe in a more unifying picture breakdowns of standard Navier-Stokes that have been noticed before and I think seen in experiment. I think Kristan and Sun also mentioned that the deep link between hydro and geometry especially illustrated with EFT, may also help us learn how to couple fractons and other kinds of exotic constrained matter to gravity. And I think what my sense is, this is sort of one of the exciting problems, for this audience, kind of the high energy side of UQM. So, and then something I'm personally interested in, but which is not UQM, so don't tell Jim Simons, is that one of the things I really hope that we can make a lot of progress in the coming years is generalizing these field theories for thermal fluids to non-thermal fluids, like flocking birds and other kinds of active matter where, I believe that the formalism I talked about for time reversal broken fracton fluids, there are sort of clear analogs of this for the systems that I've written down here. And so, I hope that soon we'll be able to release some results on this. So that's all I wanted to say. Happy now to take questions, discussions.
So thank our panelists for very stimulating overviews. So let's take questions. So I'll let John ask the first one. John, please.
Hi, thanks. I was surprised by this fact that Sun mentioned about electrons in astrophysical plasmas living in the lowest Landau level. I guess mostly for sociological reasons, that the people I know who study those things only use classical physics. Are there consequences that we can see in space of this fact? That would be amazing.
I haven't.
Yes, it's directed.
Yeah, I know a lot of people are interested in the question of what happened to electrons when in a very high magnetic field, but I'm not sure I know what kind of consequences that would be for astrophysics. The magnetic field that is available in near the magnetars are pretty high, so you can convince yourself that the electrons in the atmosphere of this object probably are all in the single Landau level. But I'm not sure about the temperature, whether the temperature is low enough.
So regarding that question, so is it possible to have some observable effects, say in neutron stars?
In principle, but yeah, but this is a question that the audience have to research.
Okay, thank you. Okay, so do you have questions from the in-person audience? Because we have first.
Thanks. So I guess flat band physics is quite popular in recent years because of the like twisted barrier graphing stuff being discovered. So one way of thinking of flat band is like taking an infinite mass limit, and in terms of this limit, we can see like if we take this limit to the Gaussian boost symmetry, we can generate the effective dipole symmetry at the end of the day by taking the infinite mass limit. But the thing that I'm thinking about is there any evidence or is there a good reason to say like indeed in these flat band materials we do have this dipole symmetries in any sense? For example, we can write down the quartic term for like Kristan write down like with second order spatial derivative about quartic in field. Is it true that this term is there for this, is responsible for these flat bands?
Yeah. So the band is flat. The fact that the band is flat doesn't require this quartic term in Kristan's talk. So the flatness of the band simply say that there is no quadratic term in the kinetic in the Lagrangian. Yeah.
More explicitly, so what kind of exotic symmetry is?
I don't know what to expect. Actually, if and there is any such symmetry. If you look at the flat band in graphene, for example, it's not. I'm not sure if one can simply concentrate our attention on a single band, because if you remember, there is also this another band that comes down to a rather small distance to that flat band. So I don't know if one can simply neglect that band. Maybe we have to take into account also the bottom of that band. Yeah.
I guess the other comment I would quickly add is that I think it's sort of an interesting prospect. I think the near-term experiment to think about sort of whether exotic symmetries can be realized in these systems or exotic hydrodynamics. I think in the near term, many of the experiments are still just trying to sort of nail down the static nature of the phase diagram. What is the nature of superconductivity versus insulating phases in twisted bilayer graphene, for example. And I don't follow along too closely, but I remember when this first got started, there were about 100 different theories for the origin of superconductivity, and maybe we cut it down by 1 order of magnitude, but I don't know if we've gotten it to 2. So yeah, so I don't know if there are sort of powerful experimental signatures, but it may take some time before the experimentalists are sort of ready to take that seriously.
Thank you. So, Umang is.
So this is technically not a hydrodynamics question, so sorry for that. But since holography was mentioned, San and Kristan mentioned that a major obstacle to that was thinking about the gauged versions of the exotic symmetry in the bulk. But wouldn't a more immediate issue just be the fact that these exotic symmetries explicitly require non-relativistic spacetimes? So how would you envision that being replicated in a bulk? Like, would you have to spontaneously break Lorentz symmetry, or is there some more explicitly broken version of gravity that could potentially reproduce it?
So I'm fortunate in that the answer to that question, I mean, this is something people looked at a lot in the days of what was called, applied ADS CFT or ADS CMT, which doesn't exist as much of a field anymore. But there were various ways that people got around this. One has to distinguish between whether the gravitational dynamics is whether what are you dividing by, what do you have an effective field theory of, and also what is the space-time background on which you are considering these black holes and so on. And the kinds of games that people played, they were able to find things that imitated, say, non-relativistic fluids with and without Galilean boost symmetry and so on, by studying, well, with Galilean symmetry, it was actually a bit trickier, but without it, you'll see papers about this still, about like Lifshitz spacetimes or hyperscaling violating spacetimes, where what you consider is a slightly more complicated gravitational effective theory. Einstein-Maxwell dilaton theory is the one that people seem to really like, in backgrounds where the boost symmetry is violated basically by the boundary conditions at infinity. So it's explicitly broken by what's going on at the boundary. You have a non-relativistic system. There's like sources turned on, if you will, for that break the Lorentz symmetry. But the dynamics is still that of ordinary gravity coupled to matter. And somehow, if there is going, I guess time will tell, if there's going to be some mock-up of these exotic symmetries holographically, it's going to have to be a bit more severe for the reason that I mentioned. That's why I focused on that the symmetries appearing on the boundary would be gauged in the bulk, and that seems to require a different theory of gravity. Maybe. Someone has to find out. I should say too, I guess that, okay, Andreas is falling asleep, but there's been a little, there's a complementary question, which is, can you embed these systems with exotic symmetry into string theory? And I mentioned Andreas because I think there's really only one paper to date on that, and he's one of the co-authors on it, engineering these things with lattices made out of stacks of brains. That's another direction.
Okay, so John is the next.
Hi, yeah, I wanted to ask Andy a question about what counts as ultra quantum matter. So the path integrals that you're building, I guess, to describe these sort of non-equilibrium fixed points of birds and things.
It's not quantum, let alone ultra quantum.
But how do you know, I guess is my question. So you're studying a path integral. How do you know that the fluctuations that you're describing with that integral are statistical rather than quantum mechanical?
Okay, so I guess, sorry, I don't mean to be flippant, but at some level, like with birds, I just don't think the birds are in quantum superposition. I mean, I think they're in a
Sorry, no, I'm not saying that at all. I'm saying there could be some other application of the same integral.
Oh, okay, fine. I don't know that for sure. I would say that the formalism we're developing in the near term, we do start from an explicitly classical starting point, but I don't know how straightforward. I mean, maybe it's quite straightforward to extend to quantum mechanics, but there are some aspects of the Schwinger-Keldysh path integrals for thermal field theories that seem to have nice explanation. Like unitarity has interesting consequences on the thermal path integrals, and I guess the closest thing to that we would have at the moment in our classical formalism is demanding that whatever sort of theory we generate leads to a well-posed Fokker-Planck equation for a normalized distribution. So maybe that's sort of similar to unitarity, and that would straightforwardly extend to unitarity in a quantum analog of the story. But
is that just like conservation of probability?
yes.
Mm-hmm.
But I don't know how simple that would be. I would be tempted to say that one can't just naively quantize what we're doing, if only for this reason, that formally there seem to be some differences. But yeah, my personal philosophy on this is that maybe this is sort of a, perhaps, I don't know how infrequent, but an example where something where we started really with quantum matter, thinking about fractons, et cetera. Maybe in the end, it will sort of lead us to a better understanding of another interesting classical problem. And then whether one can go back again is, I think, completely open.
Do we have other questions from the audience?
So I think Stan mentioned that people were looking at systems with infinitely many conserved charges. I was wondering if you or anyone else could elaborate on how you can even consider some universal hydrodynamics when you have an infinite number of conserved charges.
We have take a system of bosons. One example is a system of bosons, relativistic boson interacting with delta function potentials, the linear model. It's known to have infinite number of conserved quantities, but how this, so the thermodynamics of such a system can be solved is exactly known, but how non-equilibrium, how to extend that to non-equilibrium physics is, I think now active field of research, and I think there is a lot of commonality with hydrodynamics, but the hydrodynamics here would be more complicated because it probably would involve an infinite number of conserved equations, conservation laws, and constitutive relations. Umang has comments on that? Question?
Actually, can I just, I was going to add a quick comment on that, oftentimes what these theories look like as a starting point is kind of like kinetic theory. And you could sort of almost imagine it if you started with kinetic theory, but you demanded that the collision integral could only relax functions that had spatial dependence, but just like a homogeneous perturbation to any quasi-particle number density was a conservation law. That's maybe a sort of very naive picture for what this so-called generalized hydrodynamics of integrable systems looks like.
Yeah, so any quick question for Kristan? Since I think Kristan is heading out.
I have a quick question for Kristan.
Oh.
So if I'm not mistaken, Kristan, you've done some work on coupling fractons to curved background metrics. Does that have any implications for this question, which is still on Andy's slide, namely on coupling fractons to dynamical gravity?
Were you coupling? Not to dynamical gravity, but I think yes is a reasonable answer. Couldn't help.
Yeah, I think they're related to things that I mean, Andy has been thinking about coupling. Let's be careful with terminology here, perhaps for posterity's sake, but systems with dipole symmetry to gravity, they have a complementary viewpoint, I think, that, and I'm still sorting out maybe a couple minor details, but yeah, it is very closely related. I think the thing that is maybe a comment about it that gives some insight beyond the coupling to background, to space-time, is somehow maybe a very kind of one of the starting points for coupling models with dipole symmetry to background is an observation that even though the precise form of the dipole symmetry depends sensitively on details like what's the space on which you're living, or is there a lattice or not, in the continuum limit anyway, despite the fact that in finite volume the dipole symmetry is discrete rather than continuous, there is a word identity associated with that dipole symmetry. Usually word identities are all like, I mean, it's the particular one that I have in mind is like vector current is divergence of dipole current. That's something that you might have thought comes from a continuous symmetry, but it's there even with a discrete dipole symmetry. And that's very useful. It's maybe for reasons you can look at our paper, or we can talk over email. That's kind of the starting point for why you're even able to couple these things to background in the first place in a covariant way, despite the fact that everything I said has nothing seemingly to do with space-time. Yeah, so that's maybe one comment about that, and that there are the systems with models with subsystem symmetry. This to me seems like a much more ambitious goal than I think things will get sorted out with dipole on the scale of months, if not sooner. But with subsystem, somehow that seems much trickier. But there also you do have word identities in the continuum, things like that your Jij is like JXY, for instance, and nothing else. That you can bear superficial resemblance and may be of use. So sorry for changing the question a little bit from what you asked, Yale. Yeah.
Thanks.
So do you have?
I had a follow-up question on the about these generalized hydrodynamics with infinite symmetries. I always thought that integrable systems don't generally thermalize. So what does it mean for there to be like some kind of hydrodynamic description of systems with infinitely many conserved quantities, like even before trying to describe what that hydrodynamics is?
This system, for this system, the equilibrium, thermal equilibrium state would correspond to an infinite number of parameters, not just temperature and chemical potential, but also the chemical potential, for example, for all the conserved charges. And now you can ask, what happens if you make a system slightly inhomogeneous, where all these infinite number of charge densities or chemical potential is a smooth function of space? And it's legitimate question to ask, what are the equations of motion of these quantities? So this I would call generalized hydrodynamic equations.
Any more questions from Zoom? From in-person audience? I think we're running out of questions. Then I guess let's thank our panelists again.